Greetings, Physics 100 students. I know you've just survived the first midterm, hopefully. And now we are back for the material for the second midterm, which kicks off with the toughest chapter for the second midterm, momentum. Now, momentum is the chapter where we find out which ones of you have developed good physics habits. Those of you who have gotten the habit of putting directions with all velocities, accelerations, and forces will do pretty well here, especially if you can set up a net equation, like a net force equation or a net total momentum equation. If you leave off directions, or if you just try to grab the equation and throw numbers into it, the physics game, momentum is going to be really tough for you, because momentum requires use of concepts to be able to solve momentum problems, namely the concept of momentum conservation. It is a key concept which you'll be using again and again in momentum. Now this one's a particularly long lecture, so there'll be several parts to this one, probably 3 or 4, where some of the other ones were a little bit shorter lectures. And we have plenty, lots and lots of sample problems, because this is definitely one of the tougher chapters, actually the toughest chapter for the next midterm, perhaps the toughest chapter of the entire semester. So our goal for this next few hours is to understand momentum. Objectives were to learn about what exactly momentum is, because it's one of those ideas that we don't really picture so well. Force, we can picture someone pushing or pulling, velocity, acceleration. We can understand these things. Momentum's a little bit tougher to understand. We're going to learn about how to do calculations of momentum in 2 dimensions as well as 1 dimension. We're going to understand how momentum is changed, namely through the use of what's called an impulse. We're going to understand what the conservation of momentum is, what it means, and how it's used, and how it's very useful for us. Particularly, but how conservation of momentum could even help you win a court case. So what is momentum? This is a word that gets thrown around a lot, particularly in politics and in sports, well, political races and in sports. The Washington Redskins now have the momentum, because the other team scored 60 points unanswered, but now they scored a touchdown, so they have the momentum. Okay. That's not quite what momentum is. But what is momentum? So I want you to think about that for a moment. Put it on pause. What does the average person think about momentum and what momentum actually is? So, in the common media, momentum seems to be something to do with winning. Well, this team is winning now. They have the momentum. Well, that's not it at all. That's not what momentum is. In physics, momentum is the ability to create change. Namely, change of motion. The more momentum I have, the more momentum I can transfer to something else, the more I can change its motion. Momentum, like energy, is a variable that is conserved, so it does not change. So momentum equals mass times velocity, and total momentum is the sum of all momentum. So if I have 2 cars, the total momentum of those 2 cars is momentum of car 1 plus momentum of car 2. So let's do a quick level 1 sample. I have a car, 500 kilograms, velocity 20 meters per second forward. Now since velocity has direction, and momentum is equals mass times velocity, momentum also has direction. So this is very important to keep direction in the problem, because it is going to have direction. If you have 2 cars traveling in opposite directions, their momentums are going to have signs that are opposite. Alright, so what's the car's momentum? Go ahead and pause it and calculate, or you can probably do this one without the calculator. Go. Alright, and you're back. So, momentum, which we abbreviate with the letter P, momentum equals mass times velocity. Mass was 500 kilograms, velocity 20 meters per second forward, and we do the math, and it's 10,000 momentum units. Now what is a momentum unit? Well, there's nothing special or fancy with momentum units, but there are two choices. Either kilograms, meter per second, and direction, or newtons times seconds and direction. And it doesn't matter which one you use. You're welcome to use either one. My recommendation is if you're dealing with forces, use newtons times seconds. If you're dealing with velocities, use kilograms meters per second. Always going to have a direction. In this case, forward. All right, so that was a level 1 problem. Plug and chug. But most momentum problems aren't going to be level 1, so we'll have to do the level 1 to be able to solve the level 2. So what are the level 2 problems? What do they look like? Well, usually they're going to require a concept, namely the concept of conservation of momentum. And we'll get to one a little bit later on in the lecture. So let's do another example. So this one we have more than one momentum, so we're going to have to add up momentums, and we're going to have to watch direction. So we have two cars, 700 kilograms and 1,400 kilograms. The lighter car, 20 meters per second north. The heavier car, 10 meters per second south. Now, calculate each car's momentum, and usually when you do momentum, pick a direction and do everything in that direction. And if you have 2 dimensions, pick a direction for each dimension. And then we're going to combine those momentums to get a total momentum. Now, your answer for part B is going to be very boring. So if you get an exciting answer, you probably forgot to include direction. So go ahead and solve part A and part B now. Go. All right, so let's do the momentum of each car. This is a level 1 problem times 2. So for car 1, momentum, mass times velocity, 700, 20 meters per second north. And that's supposed to be we do the math. 7 times 2 is 14. We add 3 zeros. We got 14,000 units north. All right, so far, so good. Now, the tricky one, car 2. Don't worry, we usually only have car 1 and car 2. If I do car 54, that isn't moving. I don't think I'm allowed to do. Okay, so, second car, same equation. Again, it's a level 1 because I'm just sticking in numbers into here. 1,400 times 10 south. But now there's a problem. I'm going to do everything in the north direction. So I need to do a conversion here. I need to convert my south to a negative north. Now, having the minus sign there doesn't really do much, so I'm going to put the minus sign over here. And I get negative 14,000 units north. So when you have 2 cars going opposite directions, one of those momentums is going to be negative. If you don't watch direction and you add it up the total, you take 14,000 plus 14,000, you have 28,000, and you have grossly overestimated the total momentum of the system. Which means at the end, when you calculate the velocity of some object after a collision, you're going to be way off. You're going to be way off. And this can lead to problems. So let's do the total momentum. Total momentum is the sum of all momentums. By the way, this class is brought to you by Total Serial, Total Force, Total Momentum, Total Energy. Lots of totals. So total physics. I don't know why we don't just call it total physics. Okay. So 14,000 plus a negative 14,000 means that for B, my answer is 0. The total momentum of the system is 0. Which means that after these 2 cars collide, the total momentum of the system is going to be, well, it turns out still 0. That's usually not the case, but I just made it up for it was. All right, momentum in 2 dimensions. Momentum in 2 dimensions is exactly the same as 1 dimension, except that we now have 2 separate problems. So if we have north and west, we have a north momentum and a west momentum, and those are treated as two completely separate problems and solved individually. Kind of like having a checking account and a savings account. If you overdraw your checking account, they don't care how much money you got in your savings account, they're going to charge you 25 bucks. That's just the way it goes. All right, so how do I change an object's momentum? Momentum is neither created nor destroyed, it is merely transformed, it is transferred. So you can transfer your momentum to something else, or something else can transfer its momentum to you. And this transfer momentum is called an impulse. Kind of like the transfer of money at the bank is called a deposit or withdrawal, if it's a negative deposit. In this case, it's called impulse. So impulse is the change in momentum. So it's the final momentum minus the initial momentum. Impulse also equals mass times change in velocity. So mass times your final velocity minus your initial. And remember, always to do final minus initial and include direction. So if I throw a ball and bounce it off of a wall, the direction changes. And when the direction changes, your change in velocity is very, very large, because one of those two values is going to be negative. If the ball hits the wall and stops, my change in velocity was my total velocity. But if it bounces off of the wall, the change is now greater than all of it, because now it's coming back the other way. So in other words, if you fall out of an airplane and your parachute doesn't open, you don't want to bounce. You want to go splat. You want to go splat in as long of a time frame as possible. But then also, impulse also equals force times time. So if I apply a force on an object for some given amount of time, that's going to give me an impulse, which is going to change its momentum. The total impulse, which means your total change in momentum, if I add up the impulses for all of the objects involved in a collision, it equals 0. Okay. So I guess I left out one thing I should probably get back to for just a moment. When is a problem a momentum problem? I want you to think about that for a moment before I use some examples of impulse. We know a motion problem is a motion problem when you have distances and velocities and accelerations, and you're measuring movements. Force problems when you have pushing and pulling forces, then it's probably going to be a force problem. What is a problem in momentum problem? Well, it turns out any time you have a collision or separation, it is a momentum problem each and every time. So if I shoot a bullet out of a gun, it's a momentum problem, meaning that my total momentum is conserved. Initially it was 0, the bullet goes one way, the gun has to go the other way. Rockets are also momentum problems. Gas goes down, rocket goes up, the total momentum stays 0. A linebacker hits the opposing team's running back, that's a momentum problem. And if you're rooting for it, and if it's the Colts linebacker hitting the other guy's defender, it's a good play. For those who are on, randomly on YouTube, have you forgotten we're in Indianapolis already? Okay, guess not. Indianapolis, where all footballs are Tuesday. So, now that we have that over, let's do a sample problem for impulse. I skip over that because I gave you the answer. Okay. I gave you the equation for that. I just derived it. The derivation doesn't matter. So a car runs into a mailbox. Now this mailbox isn't cemented down. It's just on wheels, I guess. I don't know why they would put a mailbox on wheels, but this one is. So we're going to ignore things like how much energy is associated with breaking the mailbox or breaking the post. We're going to ignore that, or breaking your car. So the car hits the mailbox. You already know the mailbox is going to go flying. But the question is, how fast is that mailbox going to go flying? So that's what we're going to solve here. So the car imparts a 2,000 Newton force on the mailbox for 0.4 seconds. The mailbox is 10 kilograms, the car is 800 kilograms. And you're going to have to find a few things. Now, some of your answers to some of these questions are going to be very similar for reasons we'll get to. So find the impulse on the mailbox. Impulse. Find the final velocity of the mailbox. initial is, of course, 0 because it's at rest. Find the impulse on the car. And if you don't know how to do that, think Newton's third law. How much does the car's momentum change? That might be somehow related to the impulse. And then look at the net change in momentum. In other words, if I add up the impulse of the car plus the impulse of the mailbox, what do I get? Now, I'll warn you on the last one, your answer to E is going to be very boring. If you get an exciting answer for E, you have done something incorrectly, or you have some random number somewhere. All right, so go ahead and go. Definitely put it on pause. This is going to take a few minutes. In fact, in lecture, we usually take about 20 minutes for this. But since this is not in class, this is on the YouTube, I'm saying that like I'm 80. Okay, yes, we have the video on the YouTube. I don't know why I have the word in front of YouTube, but it's because I'm 80 anyway. Okay, sorry. So we have this video on YouTube. So I don't have to wait for you to finish. You have to pause it so you can finish. And I encourage you to do that because being able to do this is very important, although some of the problems we get to later will be more important. This is more level 1, level 2 stuff. We're going to get to level 3 stuff right away. And a lot of momentum problems are going to be level 3 because they're going to take a concept and a whole bunch of calculations, a whole bunch of bookkeeping, and maybe even a couple of equations to be able to solve. So these are definitely tough. All right, so part A. Hopefully you have them all done. Or at least you have a few of them done. You're stuck on a problem. You need to understand the concept to be able to continue. The impulse on the mailbox. Well, the equation is impulse is force times time. Force times time we're going to use here because we've got the force and the time. So I equals F times T, which is 2,000 newtons, and you can assume it's forward, even though I didn't specify that, times 0.4 seconds, and the answer is 800 newton seconds forward, or 800 kilograms meters per second forward. All right, so that's my impulse. The new velocity of the mailbox. So impulse, in addition to force times time, also equals mass times change in velocity. And I know I'm developing the bad habit of standing in front of the equation from your standpoint, even though it's not in front of the equation from mine. So impulse equals mass times change in velocity. So that's what we're going to use here. We know the impulse is 800, so we know 800 equals, this is for B, mass times final velocity minus initial velocity. Now this one was 0, so the math is going to be a little bit easier. I divide inside by the mass, and I get my final velocity. Now the mass, what mass do we use? This is one that trips people up. Because I gave you both the mailbox and the car. Which one do we use? Well, let me ask you this. Which object are we calculating the impulse on, and which object are we calculating the final velocity for? Because that's the object you need to use the mass for. Now in this case, we're doing the velocity of the mailbox, so we're going to need to use the mass of the mailbox, which is 10 kilograms. So that means my final velocity is 80 meters per second forward. 800 divided by 10 is 8. That's about 200 miles an hour. So, mailbox out of the can. Not quite realistic because most mailboxes are attached to very well-grounded things. So the car would have to break that first before it sent the mailbox flying. But in this case, the mailbox goes flying. So always tether down your mailboxes. Now part C. What's the impulse the mailbox imparts on the car? Now this is definitely a level 2 problem. Why is this a level 2 problem? Because you have to use a concept with the equation, but not a very complicated equation, so it's more of a straightforward equation. So the impulse the mailbox imparts on the car. So impulse equals force times time. We already know the time is 0.4 seconds. We have that time already. What's the force? What force does the mailbox impart on the car? Now we know the car imports a 2,000 Newton forward force on the mailbox. But what about the mailbox? Well, Newton's third law states that anytime the car impacts something else, that object pushes on the car in the opposite direction. So that means the car gets a force of 2,000 newtons backwards, or minus 2,000 newtons forward. And I'm going to do everything in the forward direction here, so I change it to forward. That's time equals, don't forget your minus sign. So minus 800 newton seconds forward. So the impulse on the car is equal and opposite to the impulse on the mailbox. And if the car hits a bar, then the impulse of the car is equal and opposite to the impulse of the bar. Even if you're watching from very, very far. Okay. Enough of that. Before I get sued by Dr. Seuss from his grave. So, now, how much does the car's momentum change? This is also a level 2 problem. Why? Because it requires a key understanding concept. This is a question where no amount of equations will be able to solve, but one concept will. So if you start off this problem with the what is happening here, you'll solve the problem without even having to figure out what the problem type is. So what is happening here? Well, the car experienced an impulse. And impulse is, by definition, the change in momentum. And so therefore, the car's change in momentum is also minus 800. Because momentum and change in momentum and impulse are the same thing. All right, net change in momentum. The change in momentum for the mailbox was plus 800. The change in momentum for the car is minus 800. If I add those two together to get the total change in momentum, I add 800 to minus 800, and the answer is 0. Now, which is that the total impulse is generally 0. Now, what does that mean? Well, that means that momentum is conserved. Momentum is conserved. Momentum is conserved. Momentum is conserved. By the way, shoot that one right after you shoot the F equals ma song. I can hear you not laughing. So, momentum is conserved. So that means the total momentum before a collision or separation will equal the total momentum after the collision or separation. So total momentum before equals total momentum after. I'll let that sink in. So if two cars run into each other, the total momentum of those two cars after the collision is the same as the total momentum before the collision. Now a lot of students will make mistakes. They'll calculate the momentum of car 1 to be the total momentum and forget about car 2, or vice versa. Or they'll set the momentum of car 2 equal to the momentum of car 1. Doesn't work that way. You've got to use the total momentum before equals the total momentum after. And each momentum is all the momentum. So this is momentum of car 1 plus momentum of car 2 before equals momentum of car 1 plus momentum of car 2 after. So M1V1 initial plus M2V2 initial equals M1V1 final plus M2V2 final. It's a long equation. That makes it a level 2. Just that equation alone. And also, it's true in each dimension. So we do this for each dimension. If you have a multi-dimensional collision, which if you're taking a trig or calc-based class, you most certainly will have a question with multiple dimensions of momentum. In this class, not so much. It'll probably be one dimension. But it'll probably be a head-on collision. All right. I don't know why I wrote kinetic energy down here. What do we doing energy? Oh. Okay, I see where I was going with that. Now, momentum is conserved in a collision. Now the question is, will kinetic energy, which is energy of motion, be conserved. Now, it turns out energy overall is always conserved, it merely changes forms. But will kinetic energy be conserved in a collision? So think about that for a moment. Give me a yes or no. I'm sorry, I didn't hear that. Was that a yes or no? I'm sorry, that is not correct. The correct answer is maybe. Wait, what? Maybe? So there are two types of collisions. There are elastic collisions and inelastic collisions. In collisions where kinetic energy is conserved, we call those elastic collisions. So energy is conserved and momentum is conserved. They're both conserved. It's very difficult to get an elastic collision. Most collisions are inelastic, meaning that energy is transferred. A car collision is almost always going to be inelastic. Inelastic just simply means that kinetic energy was not conserved. In fact, if two cars hit and stick together, it is always going to be an inelastic collision because energy is not conserved in that case. Usually you lose about half of your energy at least. But what happens to all the lost energy in the collision? Well, think about a car wreck. What happens in a car wreck? Cars are crumpled, right? It takes energy to crumple the cars. The cars are also heated. The metal is also heated. It takes energy to do that. So energy is going to other forms in a collision. In fact, if a car runs into you, you're hoping it's an elastic collision. You'll fly faster, but you won't break any bones, at least not until you hit the ground. So the only thing you need to look at to determine whether a collision is elastic or inelastic is look at the total energy, or total kinetic energy, sorry. If the total kinetic energy is not conserved, then it's inelastic. One dead giveaway is if both objects slow down, which is possible on a head-on collision, then it's definitely going to be inelastic. Most head-on collisions are inelastic. To be an elastic collision, usually it has to be a two-dimensional collision. All right, so using momentum, we can actually predict what is going to happen in a collision, or what has happened as a result of the collision, or we can figure out what happened before a collision. So let's say that you are driving down the street and you get into a head-on collision. You can actually figure out how fast another car was traveling based on momentum. In fact, that could actually help you win a court case if they were speeding. Particularly if you're doing a turn and they're speeding and they hit you. So understanding momentum is useful for when playing pool, because the balls usually momentum is conserved. Bowling, you're using the pins to knock everything down. That takes momentum. Making safety features for cars or other things because you can use momentum to make the acceleration of the passengers less. Race car safety. When a race car hits a wall, the parts fly off. This is actually a design feature because those parts that fly off take away momentum so that the car slows down because of that, so that when it runs into the wall, there's less of a change in velocity, which means that the likelihood of the driver surviving is much greater. Military, bombs, etc., you don't want your fragments of your bomb to fly off and hit civilians. So momentum is very important. In sports, of course, momentum is always important in sports. And not the momentum that the announcers use, but momentum in terms of, person A runs into person B, you can block them, and you can block them into someone else, et cetera, et cetera. Or running back runs into a defensive player running the other direction. What happens next depends very much on momentum. So, to wrap up for this hour, and then I'll pause it and send it to the third part probably. we've learned that momentum equals mass times velocity. Momentum has direction, it breaks down into dimensions. Change in momentum requires an impulse, and momentum is conserved whether or not kinetic energy is. So momentum is always conserved, kinetic energy only conserved for elastic collisions, and knowing about momentum can help us out in our everyday life. And so what we're going to do in the second part, and the next part, which I think is going to be actually part 3 possibly, depending upon how much time we took for this first part, is we're going to examine uses and calculations and solving of problems for momentum conservations. We'll throw in a few level 3 problems. A very rare case where we actually do that.